Hello everyone, thank you for seeing my presentation. My name is Jaskaran. I'm a PhD student in the Robotics Institute at Carnegie Mellon. This presentation is on my paper called Deadlock Analysis and Resolution for MultiRobot Systems. So here's the outline of this presentation. We will visit this slide every now and then, just to remind ourselves where we are. So let me begin by telling you what motivated this work. Multi-robot systems have been used for many tasks such as search and rescue, exploration, and coverage. Generally, the controllers on these robots are a combination of a task-based control and a collision avoidance mechanism. But this combination can prevent satisfaction of the original task due to conflicts. Robots may stop moving to maintain safety, resulting in deadlocks, as has been noted in these works. So we wanted to formally investigate what are the characteristics of a system when in deadlock, and how can this information be used to resolve deadlock? And this paper is an attempt to answer those questions. I want to acknowledge that our analysis is based on the safe control algorithm developed by these authors. Alright, so let me walk you through the main results we derived in this work. Firstly, we provide an algorithmic approach to analyze geometric properties of configurations of the robots when they are in deadlock. We assume that deadlocks result from using reactive optimization-based controllers on these robots. And using tools from duality theory, we analytically deduce several properties of robot configurations, and these properties indeed match our intuition. Using these deductions, one of the main results we show is that the number of geometric configurations that are admissible in deadlock is combinatorial in the number of robots. We also devise a provably correct feedback linearization-based controller for resolving deadlocks, but we only do this for a small number of robots because of this combinatorial complexity problem that I just mentioned. Okay, so let me quickly walk you through the underlying problem that the robots are trying to solve when they end up falling in deadlock. The setup is as follows. We have n robots in the plane. Let's just focus on one ego robot, that is robot I, shown in blue here. This robot's problem is to find a control UI to make it reach its goal PDI while avoiding collisions with every other robot. All these robots are acceleration controlled, so they follow double integrator dynamics. We assume that there is a user-prescribed nominal control for each robot, which is simply a PD controller. Now, we know from linear systems theory that this control by itself guarantees exponential stabilization of each robot to its goal, but it does not guarantee that the resulting motions of the robots will be collision-free. So how do we pose that requirement? We need that the distance between any two robots be at least d sub s, where d sub s is a desired safety margin. So we pose a safety index, which is pairwise for robots I and j, called h sub ij, and I and j are safe if and only if h sub ij is non-negative. H sub ij is known as a control barrier function, that is a CBF. Here alpha represents the magnitude of maximum acceleration allowed for each robot, and we assume identical bounds for all robots. Okay, so as I said earlier, for I and j to be collision-free, we require h sub ij to be non-negative. To ensure that it continues to be non-negative, we enforce this condition on the derivative of the safety index h sub ij. Ultimately, this condition gives us two constraints on the controls of robots I and j respectively, which will ensure that subsequent motions of these robots are mutually collision-free. The expressions for b sub ij and b sub ji were too cumbersome to include here, so I suggest that you take a look at the paper for those expressions. Okay, so we already had a nominal control for reaching a goal, that was UI cap, and now we have a constraint to ensure safety. So how do we mediate between the two? The way to do that is to pose a quadratic program which minimizes the deviation from the prescribed nominal control UI cap subject to the safety constraint. So in a multi-robot system, each robot I will locally solve this QP for its optimal control UI star, which will ensure collision avoidance while creating as much motion towards the goal as possible. So going forward, this is what will be referred to as the CBF QP. Now, it is this control UI star that all robots use, and so it is natural that it is this control UI star that is also responsible for deadlocks. So let's see what information we can derive from this optimization problem to figure out what happens in deadlock. Now, I just want to mention that for simplicity of this presentation, I have omitted actuator limit constraints on acceleration UI star, but the paper derives all the proofs with those constraints in consideration. Either way, with or without actuator limit constraints, the analysis is the same. Okay, so now that we have the basic framework covered, let's see how we can extract some more information about the control using KTT conditions of that optimization problem. Since the CBF QP is an optimization problem, we can infer properties of its solution UI star by looking at the KTT conditions of this optimization. Why are we doing this? Well, we want to derive some information about geometric configurations of robots, that is, their positions, which they attain by using these controls UI star. Now, we know that whenever there's an optimization problem, the first instinct is to take its dual, or derive the optimality conditions, to gain some greater insight into its solution. So what are these conditions? Well, there's stationarity, which comes from setting the gradient of Lagrangian equal to 0. There's primal feasibility, which is simply feasibility of the constraints of the QP. There's dual feasibility, which is that the Lagrange multipliers are non-negative. And then there's complementary slackness. Okay, so given these conditions, we can define the set of active and inactive constraints as follows. The set of active constraints is the set of all those indices, or robots in our case, for which the constraint is active, that is, equality holds. Likewise, the set of inactive constraints is those indices for which strict inequality holds. From complementary slackness, we know that Lagrange multipliers will be 0 for all inactive constraints, and that, together with stationarity, gives us this expression for the optimal control U star as we wanted. Now note here that the summation of J is restricted only to the set of active constraints instead of all other robots in the system, meaning that it's only active obstacles that influence the control of the ego robot. Okay, so what is deadlock? Well, the definition is as follows. We say that a robot I is in deadlock if the optimal control UI star is 0, the velocity of the robot is 0, but the nominal control UI cap is not 0. So let's deconstruct this definition now to understand it better. UI star equals to 0 means that the QP is outputting 0, so the robot is static. UI cap not equals to 0 means that the robot should continue moving because it is not at its goal. But the QP says no. Why does that conflict occur? Well, that is to prevent collisions. In other words, if the QP is commanding the robots to stop, that's because any movement will cause them to violate safety. So what do the KTT conditions look like when the robots are in deadlock? Well, UI cap equals this sum over here. Here A sub ij are vectors connecting position of robot I to robot j. Then there's primal feasibility, which says that B sub ij should be non-negative. And then we have that Lagrange multiplier should be non-negative. And then you'll have that the element-wise product of the Lagrange multipliers with B sub ij should be equals to 0. Now, this is all math, but each of these conditions has a nice intuitive explanation that is grounded in mechanics. So let me walk you through that now. Okay, so recall that when a robot is in deadlock, its optimal control, that is the acceleration input, is 0. This means that the net force on the robot is also 0, so it is in static equilibrium. Now, if that is the case, then there must be a balance of forces at play. And indeed, that is true. From the first KKT condition of stationarity, the net acceleration UI star is the sum of UI cap and this other term, and all of these add to 0. So here are the robots. The blue one is the ego robot, the blue dot is its goal. The red robots are the active robots from the perspective of the ego robot. There's active constraints, and the gray ones are the inactive robots. The first term, UI cap, represents an attractive force pulling the ego robot towards its goal. That is shown with this blue arrow. The second term represents the resultant of repulsive forces from active obstacles that are shown in red color. So remember that only active constraints matter. Those are the obstacles that the ego robot worries about for collision, and they are repelling the ego robot. Okay, so the second KTT condition relates to primal feasibility, and in deadlock it says that B sub ij is non-negative. If you look at the definition of B sub ij in the paper and assume that robot I and j are both in deadlock, B sub ij being non-negative means that the distance between I and j is greater than or equal to the safety margin d sub s. Now it turns out that if j is an active robot also in deadlock with respect to robot I, then this distance is exactly d sub s. If it is inactive, the distance is greater than d sub s. Finally, from the last two conditions, recall that the Lagrange multipliers are non-negative for all obstacles and 0 for inactive obstacles. So we can interpret these multipliers as spring constants and assume that the springs connecting the ego robot to the active obstacles. Indeed, the SI unit of the Lagrange multipliers is that of a spring constant, assuming the robots have unit mass. Okay, so far we focused on one robot in deadlock, but what if all robots are in deadlock? This is a critical case, one that we are mainly interested in, and the definition of system deadlock is just extending the definition of one robot to all robots in the system, and we call this system deadlock. We looked at several properties of one robot in deadlock, and then we posed the definition of system deadlock. Given this, we can already answer a critical question, which is that how many geometric configurations are admissible when n robots are in deadlock? The reason we care for this question is because if this number is small, then we can think about enumerating these configurations and design decentralized deadlock resolution algorithms for all those deadlock configurations. Unfortunately, that number is not small. As this lower bound indicates, there is a factorial term, meaning that as the number of robots increases, the possible number of configurations becomes extremely large. It's in fact worse than exponential because factorial overtakes exponential quickly. This is disappointing and explains why in this work we did not develop a universal n-robot deadlock resolution algorithm. But that's okay, at least we know what the underlying bottleneck is. So let us consider a small number of robots. We'll start with 2. 2 is the least we need to call it a multi-robot system. The first property of two-robot deadlock is that the system deadlock set is non-empty. We can always find candidate positions of robots 1 and 2 that will satisfy the criteria of these robots being in deadlock. This picture shows one candidate position where the robots are collinear with the goals and all forces balance along this line. The second interesting property that we already saw before is that in deadlock, the robots will be grazing each other. Now that makes intuitive sense because if there was some wiggle room between robots, then these robots could still slowly move towards each other, but then that would end up contradicting the definition of deadlock. So it is natural that once in deadlock, there shouldn't be any wiggle room between robots, meaning that the robots are exactly separated by the safety margin. And so they're at the verge of violating safety. Similarly, we consider 3 robots. Again, for 3 robots, the system deadlock set is non-empty. I have a more detailed result in the paper, but I just want to convey the idea here that there is a set of candidate states that satisfy the definition of system deadlock for 3 robots. Now, there are a total of 2 categories of geometric configurations possible. In category A, all robots are grazing each other, meaning that each robot is exactly separated by the safety margin from every other robot, while in category B, only 2 pairs are grazing each other. So let's look at deadlock resolution now. Given all these properties of 2 and 3 robot deadlock, how can we leverage them to resolve deadlock? For 2 robots case, we know that robots will be grazing each other and robots and their goals are collinear. Given these 2 observations, we can deduce that the vector connecting the robots is anti-parallel to the vector connecting their respective goals. This is the key idea behind the resolution algorithm. So what is the resolution algorithm? Well, here's the strategy. First, we let the robots use their original CBF QP-based controllers to go to their goals, as they normally would, and wait until they fall in deadlock. Once we detect the incidence of deadlock, we use feedback linearization-based controllers to rotate these robots around one another so that the vector connecting the robots aligns with the vector connecting their respective goals. It is in this phase that we are leveraging the observation from the previous slide. Finally, once this rotation is complete, we use a simple PD controller to deliver the robots to their goals. In the paper, we make sure to design all these controllers such that safety is always guaranteed throughout their execution. Okay, so let's see the videos showing this algorithm in simulation. In this video, the original task for the robots is to swap their positions. So the robots start from their initial positions, use phase 1 control, fall in deadlock. Once that is detected, they rotate around one another using phase 2 control, which is based on feedback linearization. And once that rotation is complete, they use phase 3 control to go to their respective goals. That's how these robots accomplish the swapping using the 3-phase mechanism. Similarly, for 3 robots, the primary task is for the robots to reach their antipodal positions respectively. The robots start from their initial positions, they fall in deadlock using the phase 1 control. Then, once deadlock is detected, they rotate around one another using feedback linearization. And once that rotation is complete, the control switches to phase 3, which is simply a PD controller, so that the robots can reach their respective goals. Okay, so let's wrap up. Conclusions. So in this paper, using KTT conditions, we analyzed geometric properties of robot configurations when these robots are in deadlock, and we developed a deadlock resolution algorithm for a small number of robots. In future, we're looking into ways of developing resolution algorithms that use scheduling techniques, and we also plan to extend this analysis to other reactive control synthesis methods like velocity obstacles. And with that, I'd like to thank you for listening to my presentation. Please reach out to me for any questions, and have a nice day.